Hello, this is Ranran Zhao, and currently I'm a fourth-year student at University of Waterloo. In this presentation, I will give you a brief view of my paper, Congruences and Subdirect Decompositions in Universal Algebra. So let me share the screen. Okay. So I will first provide an introduction to universal algebra by defining lattices, algebras, congruences, and other core structures. And next, I will give you a fundamental fact called Birkhoff theorem and discuss the definition of a well-defined indecomposable algebras, which is called subdirect irreducible algebra. Then Heyting algebra will be introduced as a typical example in universal algebra. The one-to-one correspondence between filters and congruences of a Heyting algebra will be mentioned. Lastly, I will use an example to show a specific way of justifying the subdirectly irreducibility of a Heyting algebra. Lattices is a fundamental concept in universal algebra, and it can be defined by two equivalent ways. We can either define a lattice as a triple L mid-join such that the triple satisfies four axioms, or we can define a lattice using the partially ordered set P such that the infimum and supremum of A and B both exist for all A and B in P. You may wonder that why these two definitions are equivalent. The key point is to define x smaller or equal to y if and only if x meets y equals x. In this way, we can always regard meet as taking the infimum and regard join as taking the supremum. From this intuitive perspective, we can always use hazy diagram to represent a lattice. For example, the 5 diagrams below on the slide represent 5 different lattices. In each hazy diagram, every point represents an element, and if 2 points are connected by a line segment, it means that these 2 elements can be compared in the lattice, and the upper element is always larger than the lower element. We just talked about the lattice. In fact, lattice is an example of algebras. Now, let's see what an algebra is. Basically, an algebra is a pair AF, where A should be non-empty set, and it is called the universe. And F is a set of operation symbols. But here, I want to skip the technical definition of F, and it will not affect your understanding. You can just regard F as a set of basic operations defined on the universe. Actually, algebra is the generalization of many algebraic structures such as groups, rings, fields, and modules. In universal algebra, we don't study these structures specifically. Instead, we explore them from a more general point of view. Later on, we will talk about the homomorphism between two algebras, but we only want to focus on those algebras with the same structures. Let's have this definition. We say two algebras are similar if the arithmetics of their basic operations are the same. For example, A and B are similar because they both have 2 nullary operations and 1 binary operation. Recall that in contemporary algebra, the quotient group is a group mod a normal subgroup, and the quotient ring is a ring mod an ideal. Similarly, now we want to define the quotient algebra. So the subset we want to mod needs to satisfy the compatibility. So we say an equivalence relation theta is a congruence if it also satisfies the compatibility. And we define the quotient algebra to be a set of all equivalent classes generated by theta. Now it's time to talk about the maps. As I said before, here we only focus on similar algebras, and a homomorphism between 2 algebras is a map which preserves algebraic structures. However, the definition of kernel seems to be different from what we are familiar with. In universal algebra, we define the kernel of the map to be a pair A and B, such that the HA equals HB. Now, let's talk about the algebra decompositions. Recall that in module theory, we can decompose a semi-simple module into simple modules, and here we can think simple modules as indecomposable modules. Similarly, recall that in the set of natural numbers, we can factorize any natural number to be the product of primes. And here we think primes as those indecomposable numbers. So, what are those indecomposable algebras? Mathematicians worked on finding a good definition for it for several years, and eventually they found a good definition called subdirectly irreducible, which we will talk about in several minutes. So before talking about the subdirectly irreducible algebra, I want you to know what a subdirect product is. A subset S of a Cartesian product of a set AIs is called a subdirect subset if every coordinate map can project S to the corresponding set AI. So intuitively, it sounds like the S can span the whole Cartesian product space. And we will have an example to explain it more specifically on the next slide. And then if a subset S is a subalgebra, and those AIs are algebras rather than set, then we call this subdirect subset as subdirect product. Nothing different just from the set to algebras. Then a homomorphism is called subdirect if its homomorphic image is a subdirect product. Notice that we often cared about the subdirect embeddings because it is strongly related to our main theorem called Berger theorem. Just now, we introduced a subdirect product, and here is an intuitive example of subdirect embedding. We have two algebras here. One is a lattice of lines 4 points, and the other is a lattice 2 cube. See, since the line can be embedded into the cube, and the homomorphic image highlighted by the yellow covers all the 3 dimensions of the cube. So, the homomorphic image highlighted by the yellow is a subdirect product, and so the homomorphic H is a subdirect homomorphism. Now, we move to the key concept, subdirectly irreducible. We use a concept called a monolithic to define the subdirect irreducible algebras. A complete lattice L is called a monolithic if there is a unique smallest non-zero element in the lattice. And we say an algebra is subdirectly irreducible if its congruence structure is monolithic. Mathematicians have a powerful result called Berger's theorem, and it says that every algebra A is isomorphic to a subdirect product of subdirect irreducible algebras. Now, you may realize that subdirect irreducible algebras plays the indecomposable role, and it reflects the regularity of a good decompositions of algebras. Hating algebra is a typical example in universal algebra. Although hating algebra have a complicated definition, I don't want you to bother too much about it. Instead, you can just simply imagine hating algebra to be like the congruence structure, because I already proved that effect in my paper that all congruences structure of an algebra are hating algebras. To explore the congruences structure of a hating algebra, we need this definition called filter. For now, you don't need to bother with the definition of filters. I would like just to highlight that filter structures can play an important role when we explore the congruence structure and the subdirectly irreducibility of a hating algebra later on. Okay, let's see. This one-to-one correspondence result gives us a clear view of a relationship between all filters and all congruences of a hating algebra. Since filter structures are easier for us to use in the proof, so using this isomorphism, we can study congruences of a hating algebra by studying its corresponding filter structures. Moreover, we can know an additional way to determine if a hating algebra is subdirectly irreducible or not. I wrote down the whole proof in my paper, and you can refer to it if you want. The results said that a hating algebra is subdirectly irreducible if and only if there exists a unique maximal element instead of one in its reduced lattice structure. This result is easy to use, and now I will give you an example. Let's look at the lattice 1 plus d. This lattice structure is shown on the left picture. And to determine if it's subdirectly irreducible or not, we know that 1 plus d is a congruence of the lattice M5, which is shown on the right. So 1 plus d is definitely a hating algebra. Then we can use our way to justify if 1 plus d is subdirectly irreducible. We can see from the left picture that if we remove the top point, then there will be no unique maximal element. So, by our method, we know that 1 plus d is not subdirectly irreducible. Then, by Berger theorem, we know that 1 plus d can be decomposed into a subdirect product of its homomorphic images. In conclusion, I introduced many results which can be used as a powerful tool for us to dig into algebraic structures, and we can have a clearer view in universal algebra. You can refer to my paper for more details if you are interested. Thank you.